Keeper 1.5, improper integrals. All right, so first let's talk about a little vocabulary. So we have convergent and divergent. To converge means that the limit of something goes to a number. It does not go to infinity. It goes to like 5 or to 2 or to whatever. It converges to some actual number, whereas an integral is divergent, or it diverges if it goes to infinity. So like if the limit doesn't exist. All right, so we have a couple different types. So our type 1 is like if our integral goes to infinity. So if I'm like going from some number a to infinity, basically we're going to take the limit of that integral from that a to t as t goes to infinity. Or we could switch it up and our limit could be going from negative infinity to some number b. And instead we're going to take the limit as t goes to negative infinity from t to b. And then you can have infinity on both sides. So I can go from negative infinity to positive infinity. And again, I can just split that up to go to some letter a, from negative infinity to a, and then from a to infinity. All right. So for our first example, we have the integral from 1 to infinity of 1 over x dx. And so the very first thing I'm going to do, because I'm going to infinity, I'm going to rewrite that as the limit as t goes to infinity from the integral from 1 to t of 1 over x dx. All right, so then I'm going to integrate that, and I have the limit as t goes to infinity of ln absolute value of x from 1 to t. Then I'm going to plug in my bounds, so I have ln of t minus ln of 1. Remember, ln of 1 is 0, so it's really just the limit as t goes to infinity of ln t. And then I plug in infinity, so I get ln of infinity, which is infinity. And because I'm getting infinity as my answer, I know my integral diverges. All right, so type 2, we could have an asymptote. So if we have like a vertical asymptote that goes to infinity, we also need to stop it at t and do the limit as t approaches that integral. So again, if your asymptote is your upper bound, then you have this top case where you have the limit as t goes to b from the left, from a to t, f of x dx. Or you can have your asymptote be in the lower bound, so you have the limit as t approaches a from the right, from t to b of f of x dx. Or you could have some asymptote that's in the middle, and then you'd have to run two integrals to solve that with two limits. All right, so here we have an example, integral from 0 to 3 of dx over x minus 1. If you notice that x minus 1 is in my denominator, and that will yield us an asymptote at x equals 1. And so again, you need to take note of that you have that asymptote. So technically, if you think of the graph of it, your graph is going off to infinity. So we have to take into account the limit. All right, so I'm going to set it up as two statements because the asymptote is in the middle. It's not just on one of my inbounds, it's in the middle. So I'm going to do the limit as t approaches 1 from the left, from 0 to t of the function, and then the limit as t approaches 1 from the right, from t to 3 of the function. So then I'm going to integrate each function, which again is going to be the same integral for each one, but we get ln of x minus 1. And again, I have those limit statements still in front with my bounds. So my first bound is 0 to t, and my second bound is t to 3. So then plugging in those bounds, I get the limit as t approaches 1 from the left of ln of t minus 1 minus ln of 0 minus 1 plus the limit as t approaches 1 from the right of ln of 3 minus 1 and then minus ln t minus 1. All right, so plugging in my value for t on my limit, I'm going to get ln of ln of 1 from the left minus 1, which doesn't exist, and then plus 0, and then I'm going to get ln of 2, and then plugging in from 1 from the right, I'm going to get infinity. And so because I got something that doesn't exist and something that gives me infinity, I know that this integral does not exist, and therefore I'm going to diverge. Now keep in mind, no matter what, if you get an infinity out once you plug in that limit, or something that does not exist, it doesn't matter how many of them you got. You get one time to get infinity, or maybe one little piece of it doesn't exist. Either way, if something like that goes wrong, well then you're going to have a situation where your integral diverges. All right, so then we have some special cases, and we call these p integrals. So anytime you have an integral of like 1 over x to some number, we have what we call p integrals. So for case 1, your integral is going from a number to infinity. And so if p is less than 1 or less than or equal to 1, you're going to diverge, versus if p is greater than 1, you're going to converge. And then case 2 would be like if I was going from 0 to some number a. Then if my p is less than 1, I'm going to converge. And if p is greater than or equal to 1, I'm going to diverge. So in example 3, it says determine whether the integral converges or diverges without actually evaluating the integral. And so immediately I notice that this is in the form of my p integral because it's just some number over x to a power. And so here I notice that p equals 3. And I also notice that the integral is going from 0 to some number a. So since p is greater than or equal to 1, I know that my integral is going to converge by my cases on the previous slide. All right, so this one, we have the integral from a number to infinity. So this is like case 1. And so I also notice it's a p integral because it's 1 or a number over x to some power. P is, in this case, is going to be 2. So since 2 is greater than or equal to 1, and we're using case 1, I know this thing is going to converge. I don't even need to set up the integral. I don't need to solve anything. I just know it's going to converge because of my rules or my cases for my p integrals.